plot. This is my initial number of A's. And if I look at number of A's with respect to time, it's just a natural radioactive decay. It's going to decay like that. If I look at B, it's going to take off, come back down. If I look at C, it's going to take off, come back down. D will do the same thing. E will do the same thing. And if I come up here initially at time goes towards infinity, all of my atoms will become F's. But I know that any particular time I can develop an equation for this. So if I wanted to develop an equation for what is the number of D's with respect to time, I know that the number of D's with respect to time, the way I develop that equation is to look at the rate of change with respect to time. And I know it's always production minus loss. In this case, where do all the D's come from? They come from C's. So the decay of C creates D's. What about the loss? The decay of D's creates E's. So I have to come up with some expression for production, and I have to come up with some expression for decay. If I look at just the decay, this would be the decay constant of E, decay constant of D times the number of D's with respect to time. This is the loss of D's that would go to E. If I look at the decay of C, I would have to have an equation for C to look to see how it decays.
I can't see that. I'm sorry, I can't see that bottom equation. It's like the bottom one, like the decay of...
This one? The decay of D's create E's, and that is easy to calculate. That is the K constant of D times the number of D's you have at any particular time. To look at the decay of C's to create D's, which is your production, this is much more difficult to create that equation, but you can do it. When you have a long-lived chain before it goes stable, there is a shortcut that you can use, and that shortcut is in your textbook. If you have your textbook, I'd like you to go to page 64, in equation 343. If you have your textbook and you have that open, you'll see an equation that starts off N sub I you see an equation that starts off like that. This is the equation that you can set up to use for any particular isotope in the decay chain. So if I wanted to look at the number of D's, this would be A, this would be B, this would be C, N of the initial number of A's that you had, And then you see two summing techniques. The first one is capital sigma. The other one is capital pi. And that mathematically tells you how you handle e to the minus lambda I t's and how you handle the lambda k's minus lambda j's. Well, all of these relate back to A, B, C, D, E, going to F in our particular case. So, what I'd like you to do, if you're so inclined for extra credit, I want you to give me the equation for the number of B's with respect to time in this particular decay chain. So you're going to come up with an expression. If I went back and asked you to do the number of B's with respect to time, you could do that because we have already done that in the problem we worked before. We know that this would come out to be lambda A So you could take that equation and you already know what B is going to be, so you could use that generic equation that has the pi's and the sigmas in it and develop this for B. What I'm asking you to do for extra credit is to show me what this equation would be for D. So we're not doing B, we're going through C, and I'm just looking at D, so I want what this equation is. Okay. If you decide to do that, that would be extra credit, and that would be due before the start of class on Wednesday. Everybody understand what I'm asking for? Any long decay chain that you have, if it started with A and went to Z, you could find the number of atoms of any intermediate isotope in the decay chain by using the formula on page 64 that is this equation. I'm asking you in this particular case to come up with the equation to find the number of D's as a function of time, substituting in for this equation.
Excuse me?
That's all I think. Yes, question?
Does the decay matter? Like, okay, so does the decay by proton or neutron or electron matter in that equation at all? Or
No.
okay.
Just like it doesn't, when I did this, it doesn't make any difference how it, what its decay product is. What you're mainly concerned is the half-lives involved. So again, if you want to try to do this, take equation 3.43, and since we already know that the number of B's with respect to time will come out to this equation, no matter how many you have in the decay chain, you can play with this equation to understand it, to come up with the B's. Once you get how that mechanism works, I'm asking you to come up with the equation for the number of D's as a function of time, manipulating this equation. This equation is just a shorthand for how you find the number of atoms of any particular isotope in the decay chain. And again, if you decide to do that, that's extra credit. I'll ask you to turn that in on Wednesday. Okay. Before I leave chapter 3, I do have a quiz that I want you to work for Wednesday, and I'm going to go and send that to you now. Okay, I've just sent you the quiz, hopefully. I'd like to go over the quiz with you quickly. Okay, Reactor Theory Quiz 6 is worth 12 points. I've given you a decay chain that includes initially A that decays to B, B decays to C where C is stable. You're starting out at time is equal to 0. The number of A's are 8 times 10 to the 20th atoms. I've given you the half-lives involved. The half-life for A is 10 days. The half-life for B is 50 hours. So I want to know how many A's do we have? How many B's do we have? How many C's do we have after 25 days? And then for extra credit for 3 points, I want to know how long does it take until we only have C atoms left, the stable atoms, and I want you to justify that. And if you put infinity, I won't accept that. So I want to know how long would it take so that effectively all the A's and all the B's are gone. So again, you can get 15 points on a 12-point quiz. Any questions on that quiz? Okay, if not, why don't we take about a 5-minute break? When we come back, I want to start some nuclear material science. I want to wrap up the section on stresses and strains. And then after that, I want to go back to reactor theory, and I want to start on chapter 4, wrap up 4. And then if we have time, I might go back and start the next section of nuclear material science, which has to do with torque. So why don't we take about a 5-minute break, and I'll see you back at, say, 1:35, and we will do some, well, finish off the stresses and strains that we're working on before. Okay, I'll see you then.